All right, let's get into it. Today, we're jumping into one of the absolute cornerstones of physics, a rule that shapes everything from a game of pool to the dance of distant galaxies, the conservation of linear momentum. Here's the game plan. We're going to start with the absolute basics. What even is momentum? Then, we'll dig into the conservation law itself. From there, we'll put it to the test with a collision, check our math to make sure it all makes sense, and finally, I'll show you why this law is, and I'm not kidding, a physics superpower.
Okay, first things first. Before we can talk about conserving momentum for a whole bunch of things, we gotta get a handle on what it means for just one single object. So let's break it down. What is momentum?
At its heart, it is just beautifully simple. An object's momentum, we usually write it as a lowercase p, is just how much stuff it has, its mass, times how fast it's going, its velocity. That's it. And super important, since velocity has a direction, momentum has one too. It's basically the measure of mass and motion.
Okay, so why is this simple little formula so important? Well, it's because it has this deep, crucial connection to Newton's second law. You see, the total force acting on an object is really just a measure of how quickly its momentum is changing. They're two sides of the same coin.
So that leads to a really interesting question, right? If a force is what you need to change momentum, what happens when you take that force away? What if there's no net force on something at all?
Well, if there's no force, there can't be any change in momentum. It has to stay constant. The object just keeps on doing what it was doing, with the same velocity. Now this should sound familiar. It's really just Newton's first law. The law of inertia. It's the same idea, just seen through this new, powerful lens of momentum.
But, that's for a single object all by its lonesome. This is where things get really, really cool. What happens when you start thinking about a whole system of things interacting? Like, say, two crates that are about to slam into each other.
And that right there brings us to the heart of today's explainer, the law of conservation of linear momentum. And listen, this isn't some handy trick for solving homework problems. This is a deep, fundamental rule about how our universe actually works.
So here it is, in all its glory. If the net, and listen to this next word, external force on a system is zero, then the total momentum of that whole system can't change. Ever. It's constant. Now that word external is everything here. So let's unpack exactly what that means. Okay, so here's the deal. Imagine our two crates are our system. Internal forces are the pushes and pulls they exert on each other. Think of that crash when they collide. But because of Newton's third law, equal and opposite reactions, those forces always come in pairs that cancel each other out from the system's point of view. Now, external forces, that's stuff from the outside world, like friction with the floor or air resistance. Those are the things that can change the system's total momentum. So if we can ignore those, momentum is conserved.
Okay, enough with the theory. Let's make this real. Let's see how this law transforms into this amazing predictive tool by looking at a head-on collision between our two crates.
Using the law is basically a four-step recipe. Step 1, figure out the total momentum of everything before the crash. Step 2, write down an expression for the total momentum after the crash, when they're stuck together. Step 3, this is the magic part. Apply the law and set the before momentum equal to the after momentum. And finally, step 4, just do a little algebra to solve for what you want to find, the final velocity. And this, right here, is the aha moment. Think about a real crash. The forces are insane, complex, and changing over microseconds. We have no idea what they are. But here's the beautiful part. We don't care. We don't need to know. This law lets us completely ignore all those messy internal details. We just look at the before picture, the after picture, and predict the outcome. It's an incredible physics shortcut.
But look, anytime you cook up a new formula in physics, you don't just blindly trust it. It's a really good habit to run what we call sense checks. You plug in some super simple situations and see if the answer the math spits out actually makes sense in the real world.
So let's try one. What if that second crate is just a ghost? What if its mass is zero? What do you think should happen?
Well, if we plug m2 equals 0 into our final equation, the math tells us that the final velocity is just the original velocity, v1. And yeah, that makes total sense. If there was nothing there to hit, the crate would just keep on going, totally unchanged. Check 1, our formula works.
Okay, let's try another one. How about a perfectly symmetric collision? Same mass for both crates, and they're coming at each other at the exact same speed. What does your gut tell you happens when they stick together?
Think about it. The first crate has some positive momentum, and the second one has an equal amount of negative momentum. So the total momentum before the collision is 0. That means the total momentum after the collision has to be 0 too. And our formula nails it. It says the final velocity is 0. They smash together and just stop cold. It's perfect.
You know, when you see it all laid out like this, it just clicks. For every simple case we can dream up, hitting a massless crate, a perfectly balanced collision, hitting a crate that's just sitting still, the formula gives us an answer that perfectly matches what we'd expect to happen. This is how we build confidence that this law isn't just a fluke, it's the real deal.
So we've proved that the law works great for these clean, simple problems. But why did I call it a superpower? Because its real power is in how it lets us tackle the messy, complicated real world.
Now, in the real world, of course, there's friction. But during something really fast and violent, like a car crash or an explosion, the forces of the impact are so huge, they completely dwarf everything else for that split second. So we can ignore friction and use momentum conservation to analyze car crashes, to figure out the recoil on a cannon, to understand how rockets fly, and even to model what happens when subatomic particles collide in an accelerator. It scales up and down. It's incredible.
All right, I want to leave you with one last really deep idea. Let's go back to another law you definitely know, Newton's third. For every action, there's an equal and opposite reaction. We tend to think of it as a totally separate rule, right?
Well, get this, they're not separate at all. It turns out, if you start by assuming Newton's third law is true, you can mathematically prove that momentum must be conserved. And if you start by assuming momentum is conserved, you can prove Newton's third law. They are literally two different ways of saying the exact same fundamental thing about our universe.
And this all points to one of the most beautiful ideas in all of physics, from the work of the incredible mathematician Emmy Noether. These conservation laws, they aren't just random rules the universe decided to follow. They are the direct result of deep, hidden symmetries in reality itself. The reason momentum is conserved is that the laws of physics work the same here as they do over there. It's a profound thought. This fundamental symmetry in the very fabric of space is made visible to us every single time two things collide.